Cool. Okay. So yesterday we were talking, we were thinking about addition reactions. We had a look at what primary, secondary, and tertiary carbo-cations were. So let's just check that we did understand all of that. Who can tell me? That first one, we've got 7 structures here, so at least half of you are going to be able to tell me something. What kind of a carbo-cation is that one? Is it primary, secondary, or tertiary? Maria? Secondary. Why is it secondary? So that carbon atom is attached to 2 carbon atoms. I think you're going to find you're correct. Good. Excellent. Let's go on. All right then. What about this one? Primary, secondary, or tertiary? Obviously look for where the plus is to work out your answer. I'm going to pick on someone, I think. All right, so yeah, go on. Primary? Let's have a look. If you're correct, you are correct. Good. Okay. What about this one here? Now it's time to pick on people. James.
Oh, thank you.
That is primary as well. Why is it primary? Only attached to one other carbon atom. Okay, I think you're correct. Fantastic. Okay. Bisma, what about this one? Primary? Any reason why?
Selective breeding and genetic modification.
So the carbon is attached to one other carbon. Okay. I think you're right. Awesome. Let's have a look. Oh, yes. We're on number 5 already. Ahmed. Secondary? Why?
Electrons provided are from 2 carbons.
Okay, so it's
I know that's something that's
the carbon there is attached to 2 other carbons. Yeah? Secondary. But you're right with secondary. You're right with the answer. All right then. Haha. Who's not said anything yet? Pranesh. What is this one here?
Primary.
Primary? Are you sure?
Yeah.
You are correct. It's like Who Wants to Be a Millionaire? Is that your final answer? Okay, there's only one more. Surely one of them has got to be tertiary, you'd think, wouldn't you? Gabby, what's that one? Tertiary, why? Okay, so that carbon atom is attached to 3 other carbon atoms. That was a good prediction, wasn't it? Well done. You know primary, secondary, and tertiary carbo-cations. Excellent. Yes, I wanted to do this as well. All right. True, false. Electrophiles all contain a lone pair of electrons. I should make Leanne do it, shouldn't I, really? Don't worry, it's okay. Jemima, what do you think? True or false? Let's see. True, you say? False. Remember, electrophiles are attracted to electrons, so they're not likely to have a lone pair of electrons themselves. Okay.
but if they were attracted to electrons, wouldn't they have a lone? That lone pair. Okay.
Yeah. Okay. Pick on someone else next. Janavi, have I spoken to you yet? Okay, you're going to have to catch up, aren't you? Nee. Number 2. True? So the carbon-carbon double bond in an alkene is an area of high electron density, correct? Number 3, electrophilic addition to alkenes proceeds via a carbo-cation intermediate. Abdullah. True? C. Correct. Bromine water can be used to test for unsaturation. Leah. True. It's true. Okay. There's only one more left. If propene reacts with hydrogen bromide, the major product is propan-1-ol. Who to pick on? I'm not sure. Nobody looks like they want to answer. You're all staring down at your books. Angie, what do you think? Do you think false? You think correct? Definitely not that difficult. So, hopefully we know by doing this all about addition reactions. It's just a little recap, really. Okay, make sure that you're all still with me. So, what I wanted to do today was about polymerization using alkenes. Okay, if you have done triple science chemistry, then you know polymerization. We know a little bit about it. Okay, if you only did combined science, you don't know much about polymerization at all. Okay, so I need to teach you. I need to remind all of you as well. So first of all, before I change the slide, what do we mean by a polymer? What is that word? Ahmed?
A series of recurring series of the same molecule.
Okay, so like a repeating series of the same molecule. Yeah, okay, that kind of makes sense. Those small molecules, does anyone remember what we call the small molecules that make up a polymer? Go on, Leah. Monomers, exactly. Okay, so polymers are long chains or long sequences of monomers joined together. Yeah? If I find my pen somewhere. Yeah, so you could think of my little circles there being the monomers and them all being joined together in a long chain. Okay? Alkenes can make these long chains, okay, in a reaction that we would call, well, they're alkenes, so what kind of reactions do they have? What do we call their reactions? Huh? Addition, exactly, okay, so they make addition polymers. There we go. So, alkenes can undergo addition reactions with themselves to form a long chain polymer molecule. The reaction is called addition polymerization. Alright? And, oh, I really didn't like that diagram, to be fair. It looks really complicated. With the R1, the R2, the R3 and the R4. Looks a bit strange, doesn't it? Go on.
I think they just put R. R.
Because R1, 2, 3 and 4 can all be different.
Okay.
Yeah? But essentially what they're saying, okay, if we take the simplest alkene, all of these R groups could be hydrogen atoms. Okay, if we take ethene. And then when they undergo addition polymerization, all of these would be H's as well. But hopefully you see the idea of what happens. Okay, the double bond opens out, breaks, and then it's able to continue to form a long chain. Okay, the brackets and the N show that there's like a unspecified number in the chain here. I'll let you write anything down you want to. Ramon? Okay. Exactly, and like I just said, so the polymer can be represented by showing the repeat units with the square brackets around it. And the N stands for an unspecified number of monomers. Seems very noisy outside today. Okay, you ready? Got down what you want? So, oh, is that right? Oh, I wanted to reset that. There we go. So, if we take ethene, the simplest one, in fact, actually this animation probably has a bit too much detail on it. We don't need to know all of the detail here, but ethene can undergo addition reactions with itself. It will form polythene. Okay, if I click play, now the actual initiation of this, it's not necessarily that important, okay? But to make it happen, we need a free radical to start the reaction off. Usually by some kind of initiator. And it will start the reaction off by creating a radical. Are you going to do that for me? Yeah, a radical that breaks the bond on one side and just forms the carbon radical on this side. And all that happens then is that we'll just move that down, okay? That free radical is then free to react with another ethene, extending the chain. And that can keep on going. Okay? Basically the chain, that radical chain, keeps propagating itself, keeps lengthening with more and more ethene on it. Okay? The fact that it started off by a free radical is not actually something that you really need to know. But the idea is that more and more ethene join together in the chain. Each time one joins, the double bond is broken. Okay? Exactly. Eventually, if two radicals come together, then the chain will stop growing. Okay? It's a bit like our free radical substitution in alkanes. Okay? Eventually, you'll get to a termination step that will stop the chain growing. And with something like polythene, because it's a random process, okay, all of those chains can be completely different lengths, okay, and you get a whole kind of jumble of different length chains, some chains that have branches on them, some chains that don't have branches on them, and even some chains that will have multiple branches on them, okay. This, however, is quite interesting. There are two different types of polythene. Okay, there is what we would call low density polythene, or polyethene. Okay, do the conditions matter? Maybe a little bit. Okay, but low density polythene is formed under high pressure, very high pressure, as you can see, at a reasonably high temperature, 170 degrees. Okay, low density polythene is the molecules have a high level of branching and the polymer chains can't pack particularly tightly together. Okay, low density polythene is generally like this stuff that we make our terrible plastic bags out of. Okay, one day, very soon, I should stop getting spinners to give me plastic bags because it is awful for our environment. Single-use plastic should be banned. So that's just my opinion, okay? It's true, Ziad. Should be banned. Anyway, that is low-density polythene. And low-density polythene is exactly as it says. It's very low density. It's also not particularly strong. I could pull this apart quite easily. Kind of. Don't laugh, I am quite strong, honestly, Ziad. Yeah, I can pull apart a plastic bag like anyone else. Just about. Yeah, did it. And the reason it is kind of not particularly strong and low density is because it has a high level of branching in those molecules. So what does that actually mean? If you think back to your topic 2, your bonding and your structure, because the molecules are very branched, why are they not particularly? Why does the molecule not end up being very strong? Or why does the polymer itself not end up being strong? What is it about between the molecules? Go on.
Is it the London forces?
It is the London forces. Carry on with that explanation. Why are the London forces low?
So because there's not a lot of electron, like induced dipoles,
Uh-huh.
so that and they don't form a lot of bonds because their electrons don't they're not close together.
Okay, because the molecules can't get close together, then the London forces are quite weak. So we might say that as there are not very many points of contact. Okay, and that's why low density polythene is particularly weak. Yes, Leanne. I don't think you need to really know the specific pressures and so on. Okay, I wouldn't ask you to go and memorize that at all. Okay. Then there's another type of polythene, which, interestingly enough, is made at a much lower pressure and a much lower temperature, but with a catalyst. And this will make high density polythene. High density polythene, as kind of suggested by the name, has a much higher density, is much stronger. Okay, in fact, I think you're probably sitting on some high density polythene right now. Your chair, not your bottom, but your chair. Okay, much stronger. So, what do you think that means about the molecules themselves? If it's going to be much stronger. Okay, let's break that down. What would the size of the London forces be if it's going to be much stronger? Okay, go on. Okay, so the London forces are much stronger because there's many more points of contact. So what does that mean about the chains themselves? Do they have a high level of branching or a low level of branching? Much lower level of branching. Good. Okay, so those conditions, you get much less branching, so the chains pack tightly together and make something much stronger. Okay. I'll just let you carry on with that for a sec. Cool. Am I okay to move the slide on? Again, you don't need to copy huge amounts down of this at the moment. I'll move it on. Hope you don't mind. So, it's not just ethene that can undergo polymerization. It would be many other alkenes as well. For instance, propene undergoes polymerization to form, not surprisingly, polypropene. If you have a look at that, okay, you've got exactly the same thing, and this is why we put R1, R2, R3, R4, okay? So all we've done is substitute out a H for a CH3 here, okay? And then when it polymerizes, exactly the same thing happens. Just the double bond opens, and the CH3 stays in the same place, okay? So nothing really has changed. All you need to do, if you're asked to change a monomer into an addition polymer, is just to open out the double bonds, draw in these open bonds, square brackets, with an N. Okay, and it's the same thing every time. It's not going to get too much more complicated than that, okay? Here we go. We could also have chloroethene. Chloroethene, again, undergoes our addition polymerization to form polychloroethene. But to be fair, polychloroethene is not generally known as that. It's known by its old name. The old name for chloroethene is vinyl chloride. And so you might have heard of the polymer that it makes, polyvinyl chloride or PVC. Yeah? Just made from chloroethene. In fact, vinyl records, which are making a comeback. Vinyl is a thing these days again. For many years, vinyl disappeared. And now people are buying records again and record players again because the quality of sound is just so much better. They're made from PVC. Yeah? It is a very tough, durable polymer. Yes?
Sir, so the CL, like, what if it was on the bottom, like the content? Like, would that still be different? Because the symmetry would still be the same.
Yeah, exactly. I mean, it wouldn't matter if you put the chlorine here and you drew it with a H there and a chlorine there. It would still be the same thing. Yeah? All of those bonds can swizzle around. Okay? So, wouldn't be a problem at all. Yeah? It's a good question. What else have we got? What else can we make? Let's have a look. Something for you to do. That's an interesting one. So, who is going to identify the alkene that has been used to make this polymer? Is it A, is it B, or is it C? Is the question. Who am I going to pick on? Jemima? C, you're going for? Let's have a check. Yes, it is. Good. There's 5 of them, so 5 people are going to get involved. That looks very similar to something we've already seen. But which one is it going to be? It is one of them. Hands are starting to go up. Maria. A. Oh, where's my pointer gone? There. Correct. Okay. It didn't matter that it was the CH3 is moved from the top right down to here. It's still made from the same thing. Okay. All you'd have to do is like flip that around, and it would make exactly the same thing. Okay. Don't get hung up on the exact orientation of it. What else we got? Oh. Which one is that? I would question why two of them look exactly the same. But Leanne, go on then. Could it be B? Have a look. It is B. I'm not exactly sure why A and C are identical. That kind of makes you think it must be B. They are identical, aren't they? It's not just my eyes. Did you not?
Yeah. I thought this one had an X-ray, the one in the water.
Okay. It's a bit weird, that one. Okay, number 4. Which one is this? Who else am I going to pick on that? Pranesh, I've not really spoken to you yet much today. Is it A? Shall we have a look? It is A. Where's my thing gone? One more. Last one. Which one is that made from? Bismuth. C. Correct. Well done, people. You can identify the monomers. Might just run through some of this. Just about uses. I wouldn't expect you to write lots of this down at all. Just some ideas about addition polymers. Okay. So low density polythene. Soft. It's flexible. It's stretchy. It melts at a very low melting point. So we use it to make wonderful plastic bags, squeezy bottles, general purpose containers and trays, and other items that need to be soft and flexible. Not sure why that's important, but LDPE has the recycling symbol 4. whatever that means. High density polythene melts at only just a higher temperature, not much, okay, just because of the slightly stronger London forces, one would imagine. But we use that to make milk bottles, detergent bottles, and rigid items like your chairs, folding tables, pipes. Okay, I'm not worried about the recycling symbol. What do you got? Polypropylene, tough and flexible. Very, very useful polypropylene. So ropes, carpets, rugs, and lots of other textiles are actually made from polypropylene. Yeah, but usually very kind of durable textiles. You can, I believe, recycle lots of polypropylene, and these days they use it to make the fibres in like winter fleeces and stuff. Yeah. No, you're not that interested by that, are you, at all? What else? Actually, quite importantly, things that need to be heated up are often made from polypropylene. So plastic items in the kitchen can't be made from polythene because they probably melt. But things that need to withstand temperatures in dishwashers, and particularly in medical laboratories, the temperature in an autoclave, which is used to kill bacteria. Okay, and some bottles, containers, other things. Again, I'm not going to worry about the recycling symbol. Oh, there you go. Polymerisation, done. Too easy, that. Okay. Just gonna. Right, folks. So, something for you to do, just to check that you've understood what's going on today. I want you to be able to, first off, polymerize the one at the top. What would the polymer look like? And then the one at the bottom, I've given you the polymer. What would the monomer look like? I'm not even worried about what the ring actually means at the moment. Okay, or the hexagon with the ring in it, I should say. That is a hexagon, by the way. It's my beautiful artwork. It is called benzene, that ring. You are right, Ahmed.
Yeah, but what sort of phase out one car, phase out one. With like 3 notes.
You don't really need to know at this point.
So I can explain.
But if you use what you already know, then you should be able to work those out. But by the looks of it, you are already done. Yeah? So let's just check. This one up here, I suppose if you follow the rule, then we'll have the 2 carbons. We'll open it out. We need our square bracket in there. And out end. What is going to go on these 4 empty spots? FFFF. Yeah? Exactly. Okay. This is an interesting polymer, this one, by the way. There's a reason that I use this one. It has a nice long name, which is PTFE, polytetrafluoroethene. But it also has a name that you may well have heard of before, a trade name. It's called Teflon. Okay? It is the most non-stick polymer that we make. It's the one that we use to coat pans, like non-stick pans, with Teflon. Okay? Which is really, really interesting because even though you've got the most electronegative element attached to this, it's basically completely non-polar because of all the fluorines. Okay? That it's completely non-stick. It has no attraction to water whatsoever. Okay? No attraction to fats or anything like that. So everything slides off it nicely. Okay, so we coat waterproof clothes with it, we coat our saucepans with it. It's a really, really interesting polymer actually. This one as well. Again, there was a reason I picked on this one, because you would have heard of this polymer. Hopefully you went back and you closed up the double bonds and then just put everything in exactly the same place as before. Wonderful hexagon. And then like that, yeah? That was your monomer. This one, the monomer here, has a modern name. Again, we haven't done the nomenclature for it yet, but it's called phenylethene. So you could call it polyphenylethene, but this monomer also has an old name which we use instead. It's called styrene. So this becomes polystyrene. Okay? So actually you've heard of loads and loads of these addition polymers. You've just never really thought about it that much before. Polystyrene we use to make polystyrene foam. It's really actually quite easy to, as you're making polystyrene, to inject air into it and make that kind of foam. High density polystyrene is also very useful as well, okay, without all of that expanded air in it. Cool. So what I think I'm going to do over the weekend, I guess, is to set you a little bit of work, because I don't really want to have to teach you about how we might deal with polymer waste. I know that sounds really lazy, but it would make for quite a dull lesson, really. How can we deal with polymer waste? So I'm going to set you some work on, show my homework about dealing with polymer waste, okay?